Okay, now that we've looked at how electrons are arranged, we're going to look at how electrons affect bonding and how atoms bond together. In simplest terms, bonding takes into account the electrostatic attractions and repulsions that are found in atoms. Atoms are composed of positive nuclei and negative electrons. Positives repel, opposites attract. So when we form a bond, when an atom forms a bond with another atom, what happens is the forces of attraction and repulsion are minimized, and a bond forms. So there is no net force of attraction or repulsion. If we look at this graphically for a very simple molecule, H2, what we find is that if the two nuclei are too close together, then the force of repulsion between the two positively charged nuclei is too big, and the nuclei fly apart, and no bond forms. Likewise, if we have two atoms that are too far apart, the force of attraction between them is too weak to hold them together. Coulomb's law. And again, a bond never forms. So there is an optimal distance where the forces of repulsion and attraction are minimized, and we get a bond. For the hydrogen atom, that distance between nuclei is 74 picometers, and when that bond forms, 436 kilojoules of energy are released per mole of bonds formed. So bond formation is always exothermic. Energy is released when bonds are formed. Bond breaking is always endothermic. It requires energy to break bonds, no matter what type of bonds they are. So we're going to look at the Lewis theory of chemical bonding, which says that the valence electrons are what controls how things bond together. Okay. In Lewis theory, atoms lose, gain, or share electrons to get the electron configuration of a noble gas, which means 8 valence electrons. So a full S and P. Okay. That can happen by transferring electrons and forming an ionic bond, or it can be done by sharing electrons and forming a covalent bond. And what controls this is something called electronegativity. We talked about electronegativity last class, or on the class before the practice test. Electronegativity is the tendency of an atom to attract electrons toward itself when it's bonded to another atom. And if we looked at the general trend, the most electronegative atom is up here, fluorine. If we look at some specific values, you see that nonmetals have relatively high electronegativities and metals have relatively low electronegativities. And that's because metals tend to form positive ions, nonmetals tend to form negative ions. So metals, especially your group 1s, do not attract electrons to themselves. Nonmetals attract electrons toward themselves so they can form, in certain cases, negative ions. So when we start looking at bond type and electronegativity difference, what we find is that if there are very small electronegativity differences, we have covalent bonds. Now, as the electronegativity difference between the two atoms bonded together gets greater and greater, from 0, which would be 2 of the same atoms, say 2 fluorine atoms bonded together, that would have a 0 difference in electronegativity. As we start moving up, the bonds get more and more polar. Okay, CH, electronegativity difference is 0.4. So anything from 0 to 0.4 we consider to be nonpolar. We consider those electrons to be equally shared. Once we get past here, when we start getting up in this region, what we find is that the bonds that form are very polar. So they have characteristics of both ionic and covalent bonds. CF is very polar. HF is very polar. And you can see between these two, we have sodium sulfide and magnesium nitride. So we have this kind of mixture of things that we might classify as ionic or covalent just by looking at the atoms that make them up. But really, we have this crossover. And then once we get up over here, these are pretty much considered to be ionic. So just keep in mind that ionic versus covalent is not an up or down, black or white thing. It's a spectrum. So gradually changing from ionic to covalent or covalent to ionic, depending on which way you're looking. Okay. If we do have polar covalent bonds, there are two ways to represent this. Okay. In a polar bond, most of the time when things are bonded together, the electrons are between the two atoms. That's what causes the bond to form. In a hydrogen atom, the same thing up here. In the hydrogen atom, the electrons are shared equally. So if we look at the electron densities, the electron cloud, we find that it's symmetrical. In polar covalent bonds, the electron cloud is asymmetrical, with the more electronegative atom attracting electrons toward itself, which means that this polar bond is polar because it has a partial positive charge and a partial negative charge because the electrons are more down at this end. We can represent this two ways with this symbology. D plus, D minus, this is a Greek lowercase delta, meaning partial positive charge, partial negative charge. Or with this arrow that goes from the positive to the negative, and you can see this is supposed to be like a little plus sign. So here's the positive end of the bond, there's the negative end of the bond. So let's look at ionic bonding briefly. In ionic bonding, we have two atoms. We have two sodium atoms and one chlorine molecule. The sodium atoms become sodium ions, and they're positively charged. The chlorine atoms become chloride ions, they're negatively charged. This has the same electron configuration as neon. That has the same electron configuration as argon. So they've now, by gaining and losing, they both have 8 electrons in their outermost energy level. Positive and negatives attract each other. They form this structure that's called a crystal lattice. And the strength of the force of attraction in that crystal lattice is called lattice energy. That is the strength of attraction between the positive and negative charges. And according to Coulomb's law, lattice energy increases with increasing charge. So negative 2 ions, positive 2 ions have stronger bonds, stronger force of attraction. They have higher lattice energy. Also, smaller ions have higher lattice energy than larger ions. So if I change chloride to iodide, the lattice energy is going to go down because an iodide ion is much bigger, so the charges are spread further apart. Okay, now let's look at covalent bonding, and we're going to start with Lewis symbols for atoms. Remember, the Lewis symbol for an atom depicts the valence electrons for that atom. And again, we're only dealing with S and P, because those are the outermost electrons, those are the valence electrons. Remember, when we draw Lewis symbols for atoms, we don't pair up electrons until we have shown 4 single electrons. The reason why we do this is because this gives us an indication of how many bonds that atom will form in a neutral compound. Carbon always forms 4 bonds, some combination of single, double, and triple, up to 4. And always 4, not up to 4, but it will always form 4 bonds. Nitrogen, 3 bonds. Oxygen, 2 bonds. Fluorine, 1 bond. So when we go to draw Lewis structures for molecules, we again look at the valence electrons. In this simple example, each chlorine atom has 7 valence electrons. Since it has 1 lone electron and 1 lone electron there, if these 2 atoms share these 2 lone electrons, now I get a pair of electrons. And when I have a pair of electrons that is shared, a bond forms. So if I look at this chlorine, it sees 8 electrons, 6 that are only assigned to it and 2 that are shared. The same thing with that other chlorine. It sees 8 electrons also, 6 that are just on that one and 2 that are shared. So that would be a single covalent bond because only 1 pair of electrons is shared. So when we go to draw Lewis structures, typically we'll represent this pair of electrons as a single dash. So that dash counts as 2 electrons. And that's called a bonding pair because that's what holds the 2 atoms together. Electrons that are associated with only one atom are called lone pairs. So each chlorine has 3 lone pairs of electrons. Here are some examples of compounds you should recall from first year chemistry. You'll notice the carbon, 4 bonds, nitrogen, 3 bonds, oxygen, 2 bonds, fluorine, 1 bond, according to their Lewis symbol. So when we go to draw these Lewis structures, and we're going to draw Lewis structures for more complex molecules and also for molecules that don't necessarily follow the octet rule, what we're doing is we're showing the skeletal structure that shows the arrangement of atoms. Okay, when we go to draw these skeletal structures, hydrogens are always terminal, which means they're on the outside, bonded to only one other atom. Halogens also are typically terminal. They don't have to be, but most of the time they are also terminal because they have that one electron, so when they form a single bond, they're done bonding. Also, when we're trying to determine Lewis structures, typically the central atom has the lowest electronegativity value. Again, does it have to always? No, but typically it does. If I'm drawing the Lewis structure for oxoacids, which are acids that contain oxygen, the hydrogen is bonded to the oxygen atom and not to the central atom, chlorine or nitrogen. So the hydrogen's bonded to one of these oxygens, that hydrogen's bonded to one of those oxygens. And then when we go to draw structures of both molecules and ions, we try to make them compact. That is, we put something in the middle and bond everything to it rather than drawing big chains. And then we also try to make things symmetrical. And what we find is that drawing compact symmetrical structures typically is a better representation. Not always, but typically. Okay, so when you go to draw Lewis structures, here's one set of kind of not exactly rules, but more like guidelines to follow. The first thing you want to do is determine the total number of valence electrons for all the atoms that are bonded. Then you draw a skeletal structure using single bonds. So connect everything with single bonds. Then you try to give everybody 8, an octet. Of course, except for hydrogen and a couple of others, Be and B. Everybody else gets 8 on the outside. If you have electrons left over after you give all the terminal atoms 8, then all the extra lone pairs go on the central atom. And the last step is if you put your terminal atoms all have 8, and then there's not enough to give the central atom 8 also, that means that there are multiple bonds, double and triple bonds in that molecule. And so you have to share more than one pair of electrons in order to use the correct number of valence electrons, but still give everything 8. And we'll be going over this in class. We'll spend most of the class looking at examples of Lewis structures and Lewis structures of various things that follow the octet and don't follow the octet. As a final note, although we use Lewis structures to represent molecules, they're not always the best representation. For example, oxygen is, any book will have oxygen, Lewis structure like that. That is the accepted Lewis structure for oxygen. However, oxygen is paramagnetic. You can induce magnetism in oxygen, as is demonstrated in this picture where this is liquid oxygen being held suspended between 2 magnets. Okay, to be paramagnetic, you have to have unpaired electrons. There are no unpaired electrons here. They are all paired up. So the Lewis structure, although it helps us understand what's going on, doesn't always explain everything. And that's what you have to keep in mind, that they're representations that help us understand things, but they're not the perfect representation in every case.